So now we have John Mark talking about monitoring strawberries. Also happens to be my favorite fruit, which I don't get in India.
Okay, hello everyone. Thank you for having me. Thank you for organizing this room. I'm very happy to be here today to discuss how we build observability in our projects at Agricool. So you'll see it's not going to be a very technical talk, but what can be interesting for you is that we're going to look at observability from the perspective of IoT and also from agriculture. Because as you will see, we basically leverage IoT technologies to grow fruits and vegetables inside cities. So first we need to talk about strawberries. I've been living in Paris these past 2 years, and most strawberries you can buy there, they actually come from Spain or Morocco. So they actually do travel a lot before they reach the store. And this is why sometimes on the top of the strawberry you might see some white circles, some white crown. It's because the fruit was harvested way too early, before its full maturation. And they do that in industrial agriculture so that the fruit can continue the maturation during transportation. And this is how they can extend the life of the product. But the issue with that is that during the transportation, the fruit is going to attack its own reserve of nutrients. And so when you buy it, it might not be that tasty, and the nutritive quality can be very bad. And of course, the second big problem with long transportation is the use of pesticides. So another technique used to extend the life of fruits, and it raises a tons of questions about the impact of that farming model on our health. So what we try to do at Agricool is to get rid of the transportation part in the farming model. So we produce fruits directly inside cities so that we can harvest them at full maturation and so that they are very tasty and very healthy. And of course, always pesticide free. And the way we do this, we buy these containers, and inside of them we set up an IoT infrastructure to grow plants and to grow fruits and vegetables. This is how it looks inside. So we always start from a blank container, and then we set up vertical columns. We can plug the plants inside these columns. We have walls of LEDs to provide the lighting and the energy for the photosynthetic activity of the plants. We also set up an irrigation system that goes through the columns. And we also have quite complex climate regulation system made of an industrial air conditioning system and a bunch of misting pumps to control the humidity in the air, and also a set of air fans to control the air circulation. So whatever we need to set up in terms of sensors and actuators to have perfect control over the condition of strawberries so that they get like the perfect setup to grow, we install it. So for example, we also install hives from bumblebees so that bumblebees can take care of the pollination of flowers. And this is also something we can control with IoT so that we can control the door of the hive and so have fine-grained control over the exposure between flowers and bumblebees. This is the end result. This is how it looks like. This one is located in Parc de Bercy in the very center of Paris. Here is another one decorated by an artist. And so now we have around 15 containers in Paris. It means that if you buy a punnet of strawberry from Agricool in a supermarket, you know that you're dealing with a fresh product. The harvesting date for the strawberries will always be on the box, so you know you're buying strawberries that were harvested the same day or the day before. And so you know you're dealing with a fruit that is fully matured and with no pesticide. We've run some analysis to compare strawberries with other strawberries from supermarket. And on average, we reach 20% more sugar and 30% more vitamin C. So pretty high nutritive quality. if you want to build something like this, you need to run a ton of research on plants. So we are running a couple of buildings in Paris where we have set up these cells for experiments. These are like smaller versions of containers. And in each cell, we can test one variable of the environment so that through trial and error, we can discover the perfect recipe for the strawberries. And to run one single experiment, it takes a bit more than 3 months because that's the time you need to grow strawberries. So it means that you need pretty good reliability during 3 months in your IoT system. Otherwise, you might mess up the experiment and your results won't be useful. And to build an infrastructure like that, you need a team of people made of a very diverse set of technical skills. So of course, we have a lot of agronomists to run the research. And so they basically discover the agronomic recipe. Then our engineers will try to build the physical infrastructure that will make that recipe a reality inside the containers. And then we have the software team made of software developers and DevOps engineers. And so our goal is to work very closely with these engineers and agronomists so that we write the best IoT infrastructure to automate these containers and make the recipe a reality. So right now we are around between 80 and 90 people and 7 developers in the software team. So let's look inside. In every container, we install a machine with a Debian instance on it. This machine can communicate with the outside through a 4G connection. And locally, it will communicate with a PLC controller. You can see this controller as a unit that centralizes all the input-output interactions with our devices, so all the sensors and all the actuators. So basically, with this controller in one place, you can read the values of all your sensors and also the positions of all actuators. And you can also forward new commands to change the position of these actuators. On the Debian instance, we can deploy our software stack. Mainly, we have a set of microservices written in Golang and a Prometheus instance. So in Prometheus, we will store time series for the values of all our sensors and also the positions of all actuators. And the main goal of the microservices is to regulate the environment in the container. So for example, we have a service for climate regulation. That service will communicate with Prometheus to read past values from sensors. So it might send an HTTP request to Prometheus to ask what's the average temperature over the last 5 minutes. And if the service sees that the temperature is far too off from our target, it will run some climate regulation algorithm. And the output of the algorithm might be some new commands for the actuators. So it might decide to change a setting in the air conditioning system or to activate a misting pump to bring more humidity in the air. So this is how you can use a PLC controller with time series to regulate inside. If we zoom out, you can see that we replicate the same infrastructure in every container, and we use Docker images to make these deployments. And then in the cloud layer, we deploy all the user-facing web apps to build observability. So all the time series from Prometheus, we centralize them into an Influx instance. We put Grafana on top of it to build all our dashboards and graphs. We also use Redash to build dashboards over SQL stored data in our Postgres instances. And we also build quite a few observability pipelines over Slack because all our employees are using it. So for example, in Prometheus, we have alert rules to tell us when there are incidents in the containers. These alert rules will be received on Slack so that we can send technical support in the container to fix things. And so in these alert rules, you might find your typical IT rules about your network, your services, CPU loads, memory usage. But you also extend the definition of rules to new layers in the IoT stack. So we write rules for the physical machinery with there, and also rules for the plants. So for example, in every water pipes in the containers, we have pressure sensors. And so the values on the sensors are in parameters, so we can detect when there is a huge change in water pressure. And so these changes, they will trigger alerts, and they might indicate that there is a leak in the hydraulic system. And so this is how we can send a plumber on site to fix it. So when we think about observability, we often think about these techniques, time series, metrics, domain events, traces, alerting, and then we apply them to different sets of abstractions. And so in our projects, what we try to do is to be very conscious about extending the application of these techniques to the physical machinery in the containers, and also to the world of agronomy and plants. And the only way you can do that successfully is to work very closely with domain experts. You need to involve the engineers and the agronomists in the process so that they can basically educate you about the domain, and so that you can discover together what are the most valuable observability pipelines to build. And when you do that, you will discover new techniques that you need to develop. So, for example, inside your containers, we have a set of cameras that take pictures automatically of the plants, and the pictures get uploaded to AWS S3, and then we have our agronomists reviewing these pictures. And so they can discover if there is something wrong with the plants by looking at the leaves, at the flowers, at the fruits. So it's very human-centered pipeline, but we'll still consider it as a full observability pipeline because it gives us really good indication about whether the system is healthy or not. And we do this type of human-centered approach in different ways. We send agronomists inside the containers to check the plants. We run testing sessions for our strawberries. We analyze water samples from the hydraulic system. And we also make a ton of measurements on the plants, like measuring the size of the leaves to see if the plants are developing correctly. So we always try to automate the pipelines as much as possible. But when it comes to plants, it's too complex, and we need to put humans in the loop a lot. So some of the specific changes with agriculture. First, we are an IoT company, so we have to manage this huge fleet of sensors and actuators, and they are distributed in different places in Paris, so it comes with its own set of constraints. Then with plants, you can get a very tough set of agronomic SLAs. So, for example, a single incident in one container may be enough to impact the full batch of strawberries. Let's say your irrigation system goes down for a couple hours. It might be enough to damage the entire production, and so have a very big impact on the bottom line of the business. And when it comes to strawberries and berries in general, it can be very tricky because flowers and fruits are super fragile. We're pretty well known in the indoor farming industry for growing strawberries because most companies, they grow herbs and salads. But with berries, you need to be very precise in terms of temperature, humidity, irrigation levels. And finally, plants are very complex. It's an illusion to believe that you can retro-engineer a plant. It's way too complex. So in practice, what this means is that if there is an incident, you cannot always tell if it has an impact on the plants or not. You can look at them, you might see some sign that it's healthy or not, but you will never get the full story because you will never know everything that's going on inside the plant. So it's always a good practice when you write a postmortem to try to measure the impact on your business, but when it comes to plants, it's just super difficult for us to do. So what we've learned by navigating these constraints is that your observability pipelines, they should always come from an intent. So you should not build them just for the sake of coping with the ongoing observability trend. And so to do that, we have this very simple framework that for us, what's valuable is to get feedback on whether we're building the right farming model. Are we going to have great fruits, enough volume, and do our unit economics make sense so that we can scale to multiple cities? And so from that definition, this is what we want to see. We want to see observations that help us react to incidents, to understand how the stories respond to the conditions we're giving them. We want also to try to predict what's going to be the yield and quality of the product, and also any insights that could help us improve the unit economics. For example, in our system, we might have a water pump sending water in the hydraulic system. If we start monitoring the state of that pump, we may discover that we don't use it that often. And so in this case, later on, we might make a decision to downgrade it to a cheaper model. And this is how we can make a unit economics decision driven by monitoring data. So let's see the framework in action. What's always super valuable for us is to assess nutrient absorptions by the plants. So basically, if a plant is absorbing its nutrients correctly, it's going to grow healthy and provide us with great strawberries. One way to do this is to use VPD metrics. VPD stands for vapor pressure deficit. And it's kind of an indicator of the intensity of the transpiration of the plant. So if you take a plant, the leaves are saturated with water, and it needs to diffuse some of that water in the air to be able to grow. And this is called transpiration. And during transpiration, the nutrients are moved inside the plants, and this is how they are absorbed. So at every stage of growth of your plant, you need the right level of transpiration intensity. And VPD is a good indicator of that. It's basically a ratio between the level of saturated water in the leaves and the level of saturated water in the air. And what's nice with VPD metrics is that it's fully automated. You've got your time series. You can build the automated reporting on top of it. You can build the alerting. And then we have other pipelines for the same concerns. So we have our cameras that upload pictures for us. And if our agronomists look at these pictures and if they see some droplet of waters at very specific times of the day, they may get very valuable information about the intensity of transpiration. We also run water analysis of a water sample from the irrigation system. And if we do that multiple times through time, we may discover some interesting long trend about nutrient absorptions. So again, some automated approach, some semi-automated approach, and we need to put experts in the loop. This is the only way we can get like the best observations for us to know that our system is working. So all of this, it relates to what we start phrasing as a domain-driven observability. So the idea that the pipelines you're building, they're not just about techniques, but they are always related to either a business objective or some knowledge from the field of agronomy. And so in practice, it means that we want our system developers to work very closely with the domain experts. On one hand, you want these experts to share their knowledge about the domain so that developers can learn about physical engineering, about climate regulation, about agronomy, about nutrient absorptions, so that the developers, they know why they're building these pipelines, and they know where they should focus and put the priorities. And on the other hand, it's nice for your domain experts to learn about the world of reliability and observability, so that then they can understand the technicality and they can put the project in the right direction. So at Agricool, we have a ton of engineers and agronomists that know a lot of stuff about time series, alerting, Prometheus, Grafana. We try to talk to them about best practices like postmortems and defining SLOs over plants. And the only way to do this is to speak the same language. So you want the wording inside your system to be the same as the one used on the field by domain experts. Because if you have some type of cognitive distance between the two, it will be very difficult to add new features to the system, and it will slow everything down. And you could also have like these miscommunications that could result in some nasty bugs. For example, if we don't have the same VPD definition, we're going nowhere. And so sometimes when we can, we go as far as enabling our domain experts to build observability pipelines themselves. So we have non-computer people, if you want, that learn about Influx, that learn to write Influx queries so that they can build their own Grafana dashboards. We have people learning about SQL so that they can use Redash and build the views over our SQL data. We even designed a web editor for Prometheus alerts so that we have agronomists that can write their own Prometheus alert rules, and it will get deployed in any container they want for them. And so it's kind of a trade-off because you are putting more people in the loop, so there are more risk for errors or not following the best practices. But on the other end, you remove the bottleneck from the small software team, and everyone learns about building observability pipelines, and you can move much faster. So in a startup, this is like kind of a trade-off that you need to navigate. So that's it for the slides. I guess my final message is that observability is not just about techniques. It's very much about the application domain. And so I think most projects would benefit from bringing domain experts in the observability journey and to teach them about the best practices. And yeah. So we are a growing startup. We are hiring. So if you like the kind of stuff we're building, feel free to send us a message. Thank you.
Thanks a lot. We have 4 minutes for questions. Please don't get up. Please only get up after Q&A is over.
Thank you for the talk. Is any of what you show here open source?
No, we don't do open. No, we're not doing open source right now, but we want to do it in the future. Right now, we're trying to figure out how to grow these plans. So we're not investing in opening stuff because we're not ready to bring that kind of quality. But we are very much looking to build some type of indoor farming community, starting in Paris and run some open source hackathon and this kind of stuff. But it's the very beginning for us. And so we really hope, like in the coming months, to bootstrap something here.
Hi, I have a question. So you mentioned there are a lot of manual work involved when your colleagues are looking at the pictures. Do you have plans on implementing, I don't know, like machine learning models to automate this process? Because essentially they're classifying, they can say it's good, bad, or they classify the disease or something happens. Thank you.
Yeah, absolutely. We started looking at it. So right now we do the manual approach basically because we don't have time to build the computer vision stuff. We see it as like a new research project because it's very hard to estimate the effort you need to put into this. Since we always have the constraint of already running research on plants, we try to remove that risk. But we could definitely, because we know the dates for each picture, we could definitely do some supervised learning about try to estimate the level of growth of the plants, try to discover this water droplet automatically. So we don't have a nicely tagged data set today, but it's definitely going to, at scale, something we want to do to make this observability pipeline better. Yeah.
How can we compare agriculture to normal farming in its effective? And how many containers do we need to cover needs of strawberries for Dubai, like, or some small town?
So it depends on what you mean by effective. If you mean by yield, volume of production?
Yes, volume of production comparatively to the normal village, is it grows?
Yeah. So it's much more productive than classical agriculture in terms of the surface you need to use. So right now we're producing between 15 and 20 kilograms per square meter per year. So it's much more than industrial agriculture in terms of the space you need to use. So what's the big challenge today is more about the unit economics and make it work, like make this investment in this big IoT infrastructure worth. So we get much better yield, but we still a way to go before making workable at a bigger scale.
So we have one more question.
Have you planned something else than strawberry?
Yes, so our stores are in supermarket, and for a few weeks now we have herbs, so coriander, basil, salads that are getting in the store. So these are more easy to produce in terms of the reliability level you need to reach in the system. And yeah, our goal is to, in the future, try to address all the main vegetables and fruits that people have in their fridge. But right now, yeah, we focus on herbs, salads, and strawberries.
Cannabis?
Sorry?
Cannabis?
No, no. Yeah,
From America or Canada, you could.
yeah, but yeah, it's a good question. Yeah. So no, this is not something we want to do today. We are not just an IT company. We are a fruit and vegetables brand. That's our project. So we are very much about food, and so we are focusing on strawberries and vegetables. Yeah.
Thanks a lot.
Thank you. Thank you.